Hello. In the context of oscillations, damping forces will refer to forces that oppose the oscillatory motion. So the usual suspects are air resistances, drag forces, frictions, and so on. So you see here a spring mass system oscillating in air. So obviously the air resistance is pretty weak for this spring mass system. So the effect of damping is not very observable. But the same spring mass system oscillating in water will suffer pretty large drag forces, and it displays the effect of damping much more clearly. So we'll be talking about the degree of damping. In theory, if it's completely undamped, then an oscillation should last forever. If there is some damping, then because the damping forces continuously saps energy from the oscillation, the amplitude of a damped oscillation will also continuously decrease over time. Do you see that this amplitude is lower than this, and this amplitude is lower than this lower than this lower than this, and so on. If you increase the degree of damping, then the amplitude will decrease at a faster rate. Maybe somehow we increase the air resistance experienced by our oscillatory system. So because of that, energy is sapped away from the oscillation at a faster rate, and therefore the amplitude should also decay at a faster rate over time. If we increase the degree of damping further, the damped oscillation looks like this. Even more damping, even more damping, even more damping, even more damping, even more damping. This one is special, This one is special. This one is called critical damping. I'll explain what is the big deal about critical damping later. So all those I've shown before critical damping, they are called light damping or under damping. Then you get the critical damping. If you increase the degree of damping beyond critical damping, you get what is called the heavy damping or over damping. And over damped oscillation looks like this. You increase the degree of damping even further, it will look like this, and it will look like this. Okay, now let me show you all the graphs I've shown you on one page. So this is the special one, critical damping. So all these are light damping, under damping, and all these are heavy damping, over damping. So can you see what's so special about critical damping? Do you realize that critical damping is the amount of damping that's just enough to kill off the oscillation completely? See, before critical damping, your disturbed system always managed to cross the zero line at least once before it dies down forever. Crosses the zero line at least once. So all the light damping still have oscillations. There's a period to talk about, right? There's a period to talk about. But if it's critically damped, the disturbed system doesn't even cross the zero line once. It just returns immediately to the equilibrium position. Now, another thing special about critical damping is actually the one that allows your disturbed system to return to its equilibrium position in the shortest amount of time. So in the light damping, as you increase the degree of damping, you notice that the disturbed system will take shorter and shorter time to recover from the disturbance. So for example, this one, it takes about this long before the oscillations die away. For this one, it takes about this long. For this one, it takes about this long. And this is the one that takes the shortest amount of time. Beyond critical damping, the time taken increases again. It takes longer time for the disturbed system to die down to the equilibrium position. So just to reiterate, so when you're having light damping, the amplitude decreases gradually over time. Critical damping is the one that returns the disturbed system to the equilibrium position in the shortest amount of time. Beyond critical damping, you get heavy damping. That's when you have no oscillation at all, but the disturbed system takes quite a long time to return to its equilibrium position. Okay, now there's another thing I have to address here. Now you have probably heard of this before, that damping increases the period of oscillation. So what's meant by that? So look at this one. This is the undamped oscillation. So the undamped oscillation has a period of T. So this grid box shows the original undamped oscillations period. Now this is a damped oscillation. It also has a period, but its period is longer than the undamped one. Get it? So meaning this period is longer than this period. But then from the diagram you can't tell, right? That's because the increase in that period is actually very, very little only. You can increase the damping further and further and further. So we know that this period, in theory, is longer than the original undamped period. But then the increase is very tiny, very tiny, very tiny. Even at this one, for such a high degree of damping, the period, which is this one, this is the period, it still looks about the same as this one. We know in theory it's longer, but in practice it's almost unobservable. And for this reason, during exams also, a damped oscillation is usually deemed to have the same period as the undamped oscillation. Now, some students, for some reason, have this misconception. They think that when we have damping, it means that this period is shorter than this period, which is shorter than this period, which is shorter than this period. Which means these students think that damping causes the period to increase during a damped oscillation. So that's the wrong understanding, alright? A damped oscillation has a fixed period. It's just that compared to the undamped one, this period is longer, but it is a fixed period. So this period and this period and this period and this period are exactly the same. They are longer only compared to this period. Get it? Alright, that's all. Ta-ta!